The Uniline division of Robert Shaw Controls Company is pleased to bring you this video presentation on the fundamentals of pneumatic control systems for HVAC. Our intent is to cover both the concept and operation of the individual devices used within a commercial pneumatic control system. This discussion will be concerned primarily with Robert Shaw devices and other related items. These include Kellogg air compressors and refrigerated air dryers, Watts regulators and filtration devices, which are manufactured by our sister companies. The principles involved in this discussion apply to competitive devices as well. Pneumatic controls are used primarily in commercial and institutional buildings. In recent years, the need for more energy-efficient control has become a major concern. In commercial or industrial buildings of a few thousand to several 100,000 square feet, efficient control of energy is vital. Additionally, these installations have varying comfort demands that may involve the control of many individual system and subsystems. Robert Shaw pneumatic control systems provide an efficient method of control used in commercial applications because they can adequately meet the changing comfort demands in increasingly complex building designs. Our controls are able to meet modern requirements for many reasons, including the ability to modulate, lower initial cost, ease of installation, and long life. The ability of pneumatic controls to modulate allows the control system to adapt to varying loads, thus provide the required degree of comfort. To illustrate the ability to modulate, let's compare it with on-off control of a damper. Suppose this damper is controlling the flow of cool air. When there is a demand for cooling in the space, the damper controls will switch from a closed or off position to an on or open position. Note the damper moving abruptly to the fully open position. This allows full flow of cool air, which could create an overcooling condition. Let's compare that to the motion of a modulating damper. Notice the slight movements rather than the sudden opening or closing. These slight movements represent a gradual response to the change in demand and allows only enough flow to meet the need. Individual pneumatic devices are generally less expensive than similar electric or electronic items, particularly damper actuators and valves. The cost savings on these individual items in a system more than offset the cost of the compressor station. Installation of a pneumatic system is often less expensive than a similar electrical system. This is particularly true in areas where building codes require all low-voltage wiring to be run in conduit. The larger the system, the more economical pneumatic controls become. A pneumatic control system that is properly installed and maintained will provide long-term reliability and savings. The purpose of this presentation is to simplify the operation of complex pneumatic systems. We'll achieve this by taking a system and reducing it to the operation and application of the individual devices. By using this simplified method and simple components, even the most complex control strategy can be achieved with reliability and accuracy. The components of a pneumatic control system includes an air supply and a mixture of controllers, relays, and switches operating as controlled and controlling units to produce a desired effect. This presentation is divided into several sections. We'll begin with the compressor station, often referred to as the air supply. The power for a pneumatic control system is derived from compressed air. Air as a power source can be compared to the supply of electricity at a given voltage, which powers an electric or electronic control system. A pneumatic control system requires clean, dry, and oil-free air. Some pneumatic controls are air-using devices and contain small orifices or openings and passageways that are subject to contamination. For this reason, the quality of air supplied to the system is extremely important. Another consideration is the required air capacity. Air capacity depends upon the pressure of the air being delivered, the volume of the receiver tank, and compressor runtime needed to achieve and maintain the required volume and pressure. Most pneumatic control systems require a constant pressure between 15 and 25 psig to operate properly. This pressure must be stable, however, will tolerate minor fluctuations when devices change position and air is bled off to the atmosphere. The volume of air required in a pneumatic control system is determined by the air usage of the devices in that system. Air volume is measured in standard cubic feet per minute or standard cubic inches per minute. Air mains and branch lines within the system must be sized to provide an adequate volume of air to remote areas without excessive pressure losses. Compressors and their receiver tanks are generally sized so that the compressor does not run more than 1/3 to 1/2 of the time. The primary system or compressor station is made up of a number of individual components to provide clean, dry, and oil-free air to the pneumatic control system. Let's take a moment and discuss the individual components of the compressor station. Compressors used for a pneumatic temperature control system are often referred to as temperature control compressors or instrument air compressors. Temperature control compressors generally run at a lower RPM. This contributes to cooler running temperatures, less oil carryover into the compressed air supply, and longer life of the compressor. A variety of sizes and configurations may be found with single compressors on smaller systems and duplex type units on larger systems to allow for alternate compressor operation. Most pneumatic systems can be serviced with a compressor rated less than 25 horsepower. Most compressors are piston-style reciprocating units. There are three basic types of reciprocating compressors: oil-lubricated, oil-free, and oil-less. The common type seen in the field is the oil-lubricated variety. Primary air intake to the compressors should be filtered to remove particulate matter found in the atmosphere. Air is heated when it is compressed. As the air cools in the receiver tank, water and oil vapor will condense, creating a liquid buildup in the receiver tank. Most of these contaminants can be removed by the automatic drain trap that should always be installed on the receiver tank. Automatic drains help reduce the need for constant attention. However, even an automatic drain should be checked periodically for proper operation. The receiver tank is also equipped with a pressure switch to control compressor operation between a pre-selected cut-in and cut-out set point. A pressure relief valve is installed to protect the receiver from pressure switch failure. The next major component in the compressor station is the refrigerated air dryer. While some older systems may not have this device installed, it is highly recommended. It is the most effective method of removing moisture from the air. Let's take a look at this component and its accessories. The refrigerated air dryer is used to further cool the air as it leaves the receiver tank. This removes any moisture that is not condensed out in the receiver tank by lowering the temperature to dew point. The damp compressed air enters the refrigerated air dryer at the inlet port. As the air passes through a heat exchanger, its temperature is reduced, condensing the moisture out of the air. This condensate is then collected in a moisture separator at the outlet of the air dryer. This moisture separator is generally a condensate drain that relieves itself of collected water. This is accomplished automatically by a float mechanism, which should be checked periodically for proper operation. Adequate service valves should be installed so that the dryer can be removed for service. The next major component in the compressor station is the oil removal filter. No matter how good a compressor is, there usually will be some minute amounts of oil carryover into the compressed air supply. Let's take a look at some typical oil removal filters. There are two types of oil removal filters. One is an absorbent type that uses a paper element to absorb oil particulates as air passes through it. The other is a coalescent type, available in either manual or auto-drain models. The coalescent type uses a fiber mesh design filter element and the spinning action of filtered air to impact oil particles on the element. The submicron droplets of oil coalesce to form larger drops that migrate to the bottom of the element. These drops fall from the element and are trapped in the bowl. Coalescent oil filters are recommended for this type of application because of their ability to remove more oil from the air supply. The last major area of compressor station design involves the filter regulators, gauges, and pressure relief valve. It is necessary to reduce this pressure down to a working level between 15 and 25 psig. This is done with a pressure regulator. Most often a combination filter and regulator is used with a 5-micron filter element. This removes particulates from the air. This pressure regulator should be sized to provide an adequate air volume at the desired system pressure. Installed on the regulator is a pressure gauge showing the downstream pressure. The regulator is set for 20 psig. Most pneumatic controls are rated for a maximum of 30 psig main air pressure. Because of this, a pressure relief valve preset for 30 psig should be installed. This valve will open and relieve any pressure in excess of 30 psig. This concludes the video material for Section 1, the air station.